Our topic for this week is how we measure distances in space. Basically, we do this by building up a distance ladder. What do I mean by this? Well, we've already talked about how we need to know how big an AU is in order to use stellar parallax. So we have this first step, which is determining the distance to Venus. Historically, is using the transit of Venus, which I'll come back to. These days is using radar ranging. And then that allows us to determine the distance from the Sun to the Earth, which we can then use as our baseline to get stellar parallax measurements, which will give us distances out to a few hundred parsecs. Once we've got that far, there are quite a lot of stars within a few hundred parsecs of the Earth, and so we can take it a step further. But before we go there, let's just review the transit of Venus and stellar parallax. So here I've got a nice image here's the disk of Venus projected onto the surface of the Sun. And how this works is really simple geometry. So the basic idea is that if you're stood at A when Venus goes between us and the Sun, then the place that the spot of Venus will be projected will be down here on the Sun. However, if you're at position B on the Earth, then the spot will be projected up here on the Sun. That means that you can have observers at A and at B, and they can measure the angle between them. They can basically say, oh, I saw it up here, I saw it down here. What's this angle? That's the same as this angle. We know this distance because we know how far away A is from B, and so we can calculate the distance to Venus. And once we've got the distance to Venus when it's between us and the Sun, we can work out all the other distances using Kepler's configuration of the solar system. In actual fact, you don't do it quite like that. So here I've got a picture of the Earth, and you've got people stood in Spain and probably in the Canary Islands, and they're looking at the transit of Venus. And what they actually do is time it, because if you're stood in the southernmost part, you'll see it slightly further up, and so you'll have this time it takes to transit, and it will take longer to transit because it's at a higher latitude on the Sun than the people in Spain, who will see it taking a shorter transit. But the difference in time will also give you this angle, and so that allows you to measure it in a much more easily measurable way than trying to measure the angle. As I said, what we actually do these days is we can bounce radar off of Venus and time how long it takes to come back, and that gives us the distance to Venus, and again we can work out the distance to the Sun from the Earth. Once we've got that, we know that the Earth now is here, it's 1 AU from the Sun, and as the Earth goes around, close by star is going to appear to move. This is stellar parallax. So if you're here, you're looking at this close by star, and it will appear in this position relative to the background stars. In 6 months' time, you're looking in a slightly different direction, and it will appear to be here relative to the background stars. And it is this change in angle, actually half the angle, that we use in simple trigonometry to determine, since we know this distance and we know this angle, we can work out how far away it is. And that is stellar parallax. But now that we've got that, we can build on it. So we can measure the distances of things, of all these stars, out to a few hundred parsecs, and then we can use that to calibrate other measures, which include main sequence fitting, Cepheid variables, white dwarf supernovae, and this is a measure of galaxies, and Hubble's law. And we're going to work through those step by step. So let's start by reviewing the HR diagram. So here I've got the Hertzsprung-Russell diagram. Temperature is increasing to the left, and luminosity is increasing upwards, and they're both in log scale. And if we just take the stars that are within a few hundred parsecs that we've measured with parallax, then we know what their absolute brightness is. We know their luminosity because we can measure their absolute magnitude. And we know what color they are from their spectrum. And so we can plot them on here, and we find that most stars fall in this zone here. There'll be the most down here, decreasing in amount as we go up here. There'll be even less here in the giant region, even less in the supergiant region, and then there'll be the white dwarfs down here. And so this is where all of these stars will be. Okay, so now let's consider star clusters. What is a star cluster? Well, this is something where you have a big group of stars that are gravitationally bound to each other. So they're moving around a mutual center of gravity, let's put it that way. And we have two different types. We have open clusters like the Pleiades, and we have globular clusters like Omega Cen. You can see this one has many more members, is quite dense, probably has somewhere around 100,000 members, whereas this one has maybe 1,000 members. but there's a lot of stars involved. And the only way you can make this happen is they have to be born at the same time. It's very hard for stars to be captured by a cluster, and so you've got to have them born from the same big cloud collapsing so that they have this mutual gravitational attraction. How do we know that they're gravitationally bound? Well, that's a good question. Basically, we can look at their motion. So just like we can determine whether a comet is going to exit the solar system or come back around by looking at its motion, you can do the same thing with stars. You can say, oh yeah, this one is moving in a way that is consistent with being in this cluster. And so they should be moving around some sort of center of gravity, but then we have to think about how do we measure the stellar motion. We've already talked about this a little bit. So you've got two components of it. You've got the real motion is this red line. You've got the transverse motion is measured by its proper motion. That's basically how these things appear to move in real time. That is, in actual, we'll watch it over a few years, has it moved relative to the background stars. And then we also have the Doppler effect to give us the radial direction, and then we can determine how the stars are moving. So we can make sure that the stars we're looking at really are part of a cluster. And so let's start with the open cluster. So let's say we've got the Pleiades here, and we're going to plot all the stars on a HR diagram. So we can take a spectrum of each of the stars so we know what temperature it is. We can measure its luminosity because we know the distance, and so we can plot them. And these ones are nearly all on the main sequence. You can see the top of the main sequence is a little bit off, and I'll come back to that in a minute. But basically you've got them all on the main sequence. You don't have any of the giants or supergiants or white dwarfs. Now let's look at Omega Cen, this globular cluster. It is very compact, very tightly bound, lots and lots of stars in it. And again, we can measure the temperature from the spectrum, we can measure the brightness because we know the distance. And when we plot these, what we see is that we only have about half the main sequence. We don't have the top half, we only have the bottom half. But we also have a whole bunch of red giants. And so this tells us something about stellar evolution, which we'll come back to next week. But this really is something that we can use to classify this, and you'll see how this allows us to then determine distances. Now, one of the things that's really interesting here is how different they look. And what I can tell you is that this one is young. So basically everything starts off over here when it's a protostar, and it comes down to the main sequence. And then eventually they evolve off and come back over here to become red giants or supergiants. In the case of the Pleiades, nearly everything's on the main sequence, so there hasn't been time, even for these very hot stars, to evolve off. These ones are just starting to evolve and go in that direction. Whereas when we go to Omega Cen down here, it's old, because these stars up here, beyond about the F-type, have already evolved over here, and so those ones have already evolved, these ones are still evolving. Okay? So we've got no red giants in the young ones, and we have lots of red giants in the old ones. This actually helps us understand evolution in terms of where red giants come in the sequence of things. So main sequence stars evolve into red giants. But it also helps us understanding that the low luminosity stars take longer to evolve because the high mass stars have already gone over here, but the low mass stars are still around. And we already talked about this, how this makes sense in terms of luminosity versus mass. Okay, so here I have another cluster called the Hyades, and here you can see, here's the main sequence. We've got a few white dwarfs and a few red giants, but not as many as we saw in Omega Cen, so it must be older than the Pleiades, because the Pleiades hadn't lost these things up here yet. These are the ones that are now over here in the red giant phase. But we haven't got all of these ones missing yet, and so it must be younger than Omega Cen. Here we have H and Kuiper, and this one's a bit of a trick, because you can see that this is basically a main sequence, but this seems to have the high end still in, and we haven't even got the lowest ones. The M dwarfs are not there yet. And in fact, these that look like red giants are actually the proto-objects. They haven't even evolved onto the red giant phase yet. The main sequence phase yet. So what we get as an evolution of objects is we have this zero-age main sequence. So basically, we talked about this in class, that the highest mass stars get onto the main sequence first, and the lowest mass stars take their time getting there. And so what we have is that as the lower end of the main sequence is just getting populated, as these things are finally becoming fully fledged stars, we're already losing the highest mass stars. They've already gone. So these highest mass stars that are the highest luminosity and they're blue are already becoming not main sequence stars anymore after 10 million years. And after 100 million years, you've lost quite a few up there. And after 1 billion years, you have already lost all of these top ones, and you've got quite a population here, and you've already started to have a population of white dwarfs down here. And then finally, after 10 billion years, and this is more or less when the sun would evolve, so this is where the sun would be, it's about to become a red giant. But you've lost all of these stars here. They're either in the red giant phase, or they've already become white dwarfs. And so we have this evolution that we can see. But you can see that even a fairly old one still has a main sequence. So you have this young object here where you've got the top end of the main sequence filled in, the bottom end is not yet filled in. And then here you've still got the bottom end filled in. So you always have some main sequence. Why is that important? Well, here you can see this is plotting a whole bunch of clusters. And there are a lot of clusters that we can use for this that are within a few hundred parsecs of the sun to allow us to do this, and we can use other measures which we'll come on to. And this is showing you that where the turnoff should be. So if you've got, if you're younger than 10 million years, then you'd still have the top end of the main sequence. If you're 100 million years old, then you'll have lost everything down to here, and then you'll get this turnoff and you'll start populating up here. If you're 1 billion years old, then you'll come down to here, and then you'll have these turnoffs. So you can see that these Coma, Hyades, Praesepe, they are all having turnoffs right around here, so a little more than 1 billion years old. And here we have this one that is M67 is even older. And then when the sun gets to here, that's when it would be 10 billion years old. So remember, massive stars evolve more quickly, and the hot and luminous stars disappear first, but you always have some main sequence. How does this help us tell distances? Well, here I want you to consider, I've got a cluster. I know that the objects are related because their motions, even if I don't know their exact distance, their motions relative to each other are consistent with them being gravitationally bound. And I plot this particular cluster. So I have a main sequence, and I have a few red giants. This is not quite right, but you get the idea. And now I just plot them. I know what my x-axis is because you don't need to know the distance to get the temperature. Remember, that's just from the spectrum. But I don't know the absolute brightness. But they're all at the same distance. So there's a small difference between the front side and the back side of a cluster, but that's like saying that, you know, the car at the end of the street is, you know, the front of it is at a different distance from the back of it. Well, yes, it is, but on average it's all at the same distance. And so we can say they're all at the same distance, so their brightness is really, you know, the apparent magnitude allows us to plot this HR diagram. And then we can compare it to one that is calibrated. And you can see here, it's offset. So what we've got to do is to say, okay, well, I know what these are in apparent brightness. How much do I have to move this by to get it to line up? And once I get it to line up like this, I can say, okay, I now know how bright these objects should be, because they should be this bright. And so I can now say that they should be this bright. This is their absolute magnitude. I know what their apparent magnitude is, and so I can work out their distance. And so this allows you to use clusters to do all sorts of interesting stellar astrophysics. And we call this method a standard candle. It's basically, if we have a way of telling how bright something is by some measure other than its light, other than how bright its light really is, then it's called a standard candle. So you can basically say that, you know, all stars that have the same spectrum of as the sun and have the same size as the sun must be like the sun, and therefore you can work out how bright they should be. They should be one solar luminosity. But it's hard to do it for one object, and so you take a cluster of them, and then you can be sure that even if you get some small deviations, you actually get the true brightness worked out. And so the standard candle is something that will apply as we go along. This is another one that we can use, which is to do with variable stars. So here I have, if you look closely at this, you'll see that there are stars that are changing brightness. So, and they will change brightness at different rates. This is actually a cluster. So you can use this, if you've got a cluster of a few thousand or 100,000 stars, then you're going to have a few variable stars. And so you can also use this method to check that your main sequence fitting works. Okay, so what is this method? Well, it's called the Period-luminosity relation. And basically, this was Henrietta Swan-Leavitt, who was one of the famous Harvard computers, the women hired to work through data on stars. And she basically figured out that for stars that we knew the distance to, that there was a relationship between the period of pulsation, that is how long it takes to go from bright to faint to bright again, and how bright it really is. So we've got a bunch of these. We know how far away they are because we've got them with stellar parallax, and then we're watching them going bright and faint and bright again, and then we plot it and we say, okay, if I've got a pulsation period of 5 days, it's got a luminosity of 1,000. If it's got a pulsation period of 20 days, then it's more like 50,000, and so on. And so we've got this slope here that you can see. There's a really nice relationship. And basically what it tells you is that for a Cepheid variable, if you can measure the period, how long does it take to go from bright to faint to bright again, then you know how bright it really is. If you know how bright it really is, then you can work out how far away it is. And it's a standard candle again. And like I say, you can use this to measure the distance to a cluster, so you can make sure that your cluster main sequence fitting is also giving you the same answer. The other thing is that this is in solar units, so we're talking about things that are over 100 times the brightness of the sun and up to 10,000 times the brightness of the sun. And that means that instead of only being able to see out to distances of a few light years, we can now, a few parsecs, a few hundred parsecs, we can now see out to a few tens of million parsecs. So we're able to use this to measure out to large distances. Okay, so now we can measure the distances. Here I've got 1 million parsecs. Okay, so anything that is within this distance, so basically within our local group of galaxies. Here I have the Milky Way, and then we have all these little galaxies that orbit the Milky Way, large and small Magellanic Clouds, Sagittarius Dwarf, and so on. They're all small galaxies that orbit our own. Here's Andromeda, M31, and all these small galaxies that orbit Andromeda. And all of these galaxies are things that we can measure the distance to using the Cepheid variables. And we can see those Cepheid variables at these distances because they are bright enough to be able to see at a megaparsec. And that brings us to the next standard candle. And the next standard candle is the supernova. So here I have a picture. This is a galaxy, and this is a supernova. And when the supernova goes off, and only for a short period, but when the supernova goes off, it is as bright as a whole galaxy, which means you can see it from a really long distance, which makes it a really useful standard candle. Okay, so what's good about supernovae? Well, it turns out that there are enough galaxies that we can measure the distance to with Cepheids or main sequence fitting, that we actually have a decent sample of supernovae that we know the distance to. Supernovae are not that common, but there are enough galaxies that we can measure the distance to, and then they happen in that galaxy, so we know how far away they are. And that means we know how bright they are. And it turns out that there is a strong relationship between their light curve and their absolute brightness. What I mean by the light curve is, you can see here, this is actually one supernova looked at in different bands. So this is U band, B band, V band, R band, and I band. And this object, you can see even in these different bands, it's looking quite different. The spots are data, the lines are models trying to understand the data. And you can see how you get a rise in brightness very rapidly. This is usually considered day 0 because that's the peak, and then it drops off. Okay. Now here I have, this is a whole bunch of different supernovae. These are the official names of them from 1991 through to 1999. This isn't all of them, this is a selection. You see how they have different slopes, they have different brightnesses. So this is the absolute brightness. This is in ergs per second, which is like watts, only smaller. It's CGS units because astronomers are annoying. So, you know, we're talking about 10 to the 50 watts up here. And you can see how the shape of the curves are different. And basically there is a strong correlation between the shape of the curve and its absolute brightness. So once we have a supernova, we can watch how its light changes over time. So we can see, oh, it peaks here, and now it's dropping off, and it's dropping off, and it's following this path. Then we know how bright it was at its peak. And if we know that, and we've got the observation of how bright it appeared to be, we can now say, oh, I know how far away it is, because I know how bright it looks, and I know how bright it really is. I want to clarify, there are different types of supernovae. We haven't really covered this yet. This is specifically for type 1a. We'll come back to what the difference between the different types of supernovae are. But this is a summary of what we've just gone through. That basically, you've got supernovae are really, really bright, even compared to Cepheids. And they're more than 100,000 times brighter than the Cepheids. And the Cepheids were already 10,000 times brighter than the Sun. Remember, we have a 1 over r squared dependence, so we can see them 500 times further away. But that means that we can actually see out to about a gigaparsec, which gives us a huge area, but we're reliant on there actually being a supernova for us to see. And so we're able to use this to map out a significant part of the universe and work out how far away galaxies are. Okay. Now, the next one is called the Tully-Fisher Relation, and this is about galaxies, and this is basically saying, I'm here, I'm stood watching a galaxy. The galaxy is edge on, and so as it spins around, the side approaching me is going to be blue shifted, because the Doppler effect will blue shift all of those things that are moving towards me. All of this side is moving away from me, so all of this stuff is going to be red shifted, and the stuff in the middle and going across this way won't be shifted at all. And so if you're looking over here, it's going to be blue, in the middle it's going to be unshifted, and on this side it's going to be red shifted. And this allows us to determine how fast the thing is moving. Now, what is it that we're actually going to measure? Because we need to have something that is the galaxy moving and not just individual star motions within the galaxy. And it turns out that there is something we can do in radio waves, which is neutral hydrogen. Most gas is just hydrogen atoms that's completely neutral, it's not ionized. It's cold, so it's not really doing much. And cold neutral hydrogen exhibits an emission line at 21 centimeters. So we can use that to trace out the density of material and also its motion. Now, the question is, why does cold neutral hydrogen give off radio waves? It's actually to do with the structure of atoms and the fact that electrons and protons have spin. So here we have a proton and it's spinning this way, and an electron is spinning this way. It would be in a very slightly lower energy level if this electron flipped upside down. So now it's flipped upside down, so it's spinning the other way. So the proton is still spinning this way, but now this one's spinning the other way. And that makes it very slightly more lower energy. And the electrons will spontaneously do this, and so you get a photon emitted. Actually, one photon doesn't help you, but there's a lot of hydrogen out there, and so we can see the emission from this hydrogen. So what you get is, you've got this spinning disk. As you're looking at it, you're going to have a line width, which is that you're going to have some contribution to the 21 centimeter line here, which is at the rest frame, but you're going to have some that's blue shifted and some that's red shifted, and so what you get is this broadening out. And so if you measure this width, that's actually a measure of how fast this thing is spinning. And then, since we can measure the distance to galaxies using Cepheids, using main sequence fitting, and using supernovae, we can show that this width that you get is actually correlated very well with the absolute luminosity. So what is the total brightness of a galaxy? How wide is this line? And if we plot them again, we get a really nice correlation. Now, the reason behind this has to do with the fact that the more mass you have, the faster you can spin, and the more mass you have, then the brighter you're going to be, because that's what is the mass is what gives you the stars, and the stars is what gives you the luminosity. And so there's a fairly simple understanding of it. But even without an understanding, this is an empirical law that this width is correlated with the absolute brightness. So we have another standard candle. If we can measure this line, and we can measure how wide it is, then we can work out how bright it really is, and then we can work out the distance. Okay, so we've managed to come up with several different ways that are using the previous steps on the ladder to make further and further steps out into the universe, and we're now able to look at, so that local group that we looked at before is just this. And we have these other groups around us, and now using supernovae and the Tully-Fisher, we can actually measure a huge area of the sky and be able to get distances out to tens of megaparsecs. And so what's next? Well, the next thing has to do with redshift. So here I have some spectra of galaxies, and here you can see this is one that's not moving, and this is one that is moving away from us, and you can see it's redshifted. All of these lines are moved over, and then this one's more redshifted, and this one's even more redshifted, and so on. So what? Well, this is just another view of this. You can see here how the shift relates to the wavelength. Okay, so this brings us to Hubble's law. What Hubble did was he looked at the spectra of various galaxies, actually 5 galaxies, for which the distance was already known. So there are the 5 galaxies. He measured the recessional velocity, that is the redshift, and he knows the distance because he's got Cepheids or whatever that's giving him the distance, and finds this really nice trend. And what this says is that there is a simple relationship, a linear relationship, between the distance of a galaxy and its recessional velocity. And as he added more and more objects, he found that this continued to happen. And so he came up with Hubble's law. And Hubble's law is basically just the equation of that line. The recessional velocity is given by a constant times the distance. And that h0 is Hubble's constant. And at the moment it's somewhere around 70 kilometers per second per megaparsec. But what it means is that if you've got the redshift of a galaxy from taking a spectrum, then you know how far away it is. But this particular measure only works for very distant galaxies. And I'll get to that very shortly. Okay, so now we've got that we can use radar ranging within the solar system, and then we've got parallax takes us out to our local area within our galaxy, and then we've got main sequence fitting and Cepheids, which take us out a bit further, and then we've got the Tully-Fisher and the supernova light curve, which takes us out to 1 billion parsecs. And then we can use all of these to get Hubble's law. And this allows us to measure distances to all sorts of different objects. Turns out then that the hardest thing is to measure distances to things in our own galaxy and that are, not associated with a cluster or whatever, because they're too far away to use parallax, but they don't have enough information. They're not Cepheids, and they're not in a cluster, and so it's actually really hard to measure their distance. And so here we have what is basically a summary of this. So close by we use parallax out to a few hundred parsecs. And then we can use spectroscopic parallax, which is actually kind of similar to the main sequence fitting, which is not mentioned on here, but this is basically the range of main sequence fitting here. So we've got some overlap. We've got these ones get to calibrate this section. Spectroscopic parallax, say that 3 times fast when you're drunk. This is basically using the MKK classification, luminosity classification, where you use a line width to determine whether it's a supergiant or a giant, and then you've got a rough estimate of its brightness, and then you know how far away it is because you can measure its, you can say this is where it should be on the HR diagram. Okay, so now with the spectroscopic parallax and main sequence fitting, we can now calibrate the Cepheids, and so we've got this overlap here in this 1 to 10 kiloparsec range, and so now we've got these Cepheids, which takes us out to distant galaxies, and those distant galaxies then let us use the Tully-Fisher and the Supernovae, and then we can also get Hubble's law involved. And so this is how we measure distances in space, and this is what we will be doing our term papers on.